wherever you are in some time zone on the earth. It's my pleasure to say a few words here as a brief introduction to this webinar. As the president of ISPRS Commission 3, dedicated to remote sensing, I would like just to recall a few information. The first one is that Commission 3, as all the 5 commissions of ISPRS, technical commissions, Commission 3 is divided in a number of working groups. And if you're interested, please look at the website under the ISPRS website and identify if you're interested to joining these groups. And one of these the most active and productive groups in this environment is working group number 9, dedicated to health issue and geotechnologies. So congratulations to Professor Murali Krishna for organizing this series of webinars. I'm very happy to see that this is already the 4th webinar every month, and every month we have a very interesting set of 2 conferences. So congratulations, it's my pleasure to open it. Thank you also to the student consortium. Lakshmi Thapa and her team are very useful with their help on organizing this event. The other information I wanted to give you on behalf of Commission 3 is that the midterm symposium, which is the most important meeting during the 4-year terms of all commissions between 2022 and 26. This year we have the midterm symposium, which will take place in Belém, Brazil, which is my home city, in November. So for this information, also please look at the website and note that the submission deadline, which was initially scheduled April 15, which means very shortly, has been postponed to April 26, so that you have the opportunity, you have 2 more weeks if yourself or people from your team are interested in sending contributions. So back to this webinar, once again, it's my pleasure to see that this series is going well. And I think that it's time for me to give the floor to Professor Murali Krishna, who will now present the speakers and introduce this webinar. Please.
Thank you, Professor Laurent. Thank you, Dr. Lakshmi Thapa. And I welcome the 2 eminent speakers, Dr. C.K. Shum and Dr. Dayasagar, for today's webinar. To start with, we'll have the presentation by Dr. C.K. Shum. C.K. Shum is a professor and distinguished university scholar in the Division of the Geodetic Sciences at the Ohio State University, USA, and also he's a fellow of American Association for Advancement of Science and fellow of IAG. And one of the most unique item which is of very significance is he has contributed to the 2007 Nobel Peace Prize as a lead author to the 3rd IPCC assessment, which was awarded jointly to IPCC as well as Al Gore. So Professor Shum focuses on the interdisciplinary aspects of satellite geodesy and earth sciences research, including what you call as sea level changes and climate science, gravity modeling and deep learning-based climate-induced hazards monitoring, and he has published more than 380 papers and a distinguished scholar. And his specific topic related to the satellite geodesy, climate action sentinel for hazardous monitoring. We are all quite aware that climate change is increasing disaster risk in a number of ways, and it changes the magnitude and frequency of the extreme events. And so today, we don't have specifically the climate change and disaster management communities have being operated in more or less in isolation from each other. And this type of interaction, presentation, and discussion will motivate joining together for leading towards a more meaningful climate change adaptation and disaster risk reduction strategies. And he, as a professor of satellite geodesy, he is involved also in the science of measuring and understanding the Earth shape, orientation, and the gravity field. The geodesy, as everyone knows, many of people know, is a branch of the Earth science to determine the exact position of the geographical points. So essentially, he is addressing this particular aspect because geodesy is the science of measuring and representing the geometry and the gravity and the spatial orientation of the Earth in a three-dimensional field. So I specifically request Dr. C.K. Shum to give a state-of-art review and significant contributions in the area of climate action sentinel for hazards monitoring. Dr. C.K. Shum, please.
Thank you very much. Hope everybody could hear me. Thank you to the committee for inviting me and Professor Yang Ki to give such a elaborate basically introduction, and I shouldn't have make it so long. And so I will proceed, and then my slides could be a little bit longer. However, I would try to slow down and so on, maybe skip over some of them, and hopefully you'll be able to lay down if you wish, could ask questions. First of all, I just want to acknowledge some of the funding agencies, former and prior National Science Foundation, NASA, NOAA in the US, and also United States Agency for International Development. Actually, it's from India for the forest project that we have. So I'll proceed. So Professor Yankee already introduced satellite geodesy for those of you who are not really familiar with it. It's basically using the same thing. I call everything remote sensing active or, for example, passive. So I actually would be including some applications for optical multispectral satellite images for hazard monitoring. So let me, I guess I have to use. All right, so this is sort of the title, and for hazard. So what I wanted to do is to sort of, although I would like to be science first or applications first, and we use everything we have, which is observation, of course, embedding theory and technologies, probably including machine learning and other things. So the first category is the so-called satellite altimetry, and I'll just very briefly talk about it, and then you'll be jumping to application when the time comes. So radar altimetry has these 30 years of basically climate records, so to speak. Actually, it's not only over the ocean, lakes, lands, and then I'll be showing you some perhaps innovative or new applications over solid Earth. And of course, this ISAT-2, and then another one that I did not put it on there is like SWOT. So it's wide SWOT altimetry. So these top panel over here is like Global Positioning System, or broadly called GNSS, Global Navigation Satellite Systems, to accomplish, to be implemented basically by the world community, that all the data are practically free. On your right-hand side is very new, but it has been exists actually for a while. It's called sort of reflectometry, or on the right-hand side, if you have a GPS stations sitting on the ground on Earth, the reflected signals, which otherwise would be noise, and we call them signals of opportunity. So this is, if you're familiar with radar, it's L-band. However, it's not limited to L-band, but I won't cover the other bands, for example, perhaps KO band and perhaps P-band, which penetrates. All right, so most of you are more familiar with these optical multispectral. So be highlighting, well, of course, Sentinel-2, the data are practically free, and the Planet, they have probably 200 numbers changes, 3 UQ sets that theoretically take an image every day on any part of the Earth. At least that's their advertisement. And the data actually could be available for scientific collaboration and applying. So it's practically free. And then this other category is called synthetic aperture radar, or SAR, is actually could be used for classification, many other. So I will run through very briefly actually on this topic over here. For example, Sentinel, starting from Sentinel-1A and 1B, all the data are practically free. And then NASA and India, ISRO will have the so-called NISA L-band to be launched quite soon. All right, so the other one other technology is basically also radar. Come to think of it, it's a satellite to satellite tracking, so you could actually get at the gravity field changes on Earth that we correspond to Mars transport. So we have the GRACE on the right hand side. It's a mouthful. It's called Gravity Recovery and Climate Experiment, and its follow-on satellite is on its left, and then there are different nations, United States, European ESA, European Space Agency, and also China. They will be launching these kind of satellite concepts, events. So I'll be talking about the applications of practically all these with the focus that we wanted to see whether we could monitor hazards. And the hazards, what I'm talking about, arguably is due to climate change. So climate-induced hazards monitoring. All right, let's do this kind of quickly. So if you notice the April 12th, so NASA like to advertise their satellites. Of course, European Space Agency, France, India, China, many satellites. We are interested, our group is interested in data which is practically free, right, for basically scientific research. But I note that later on I'll put an emphasis on many commercial satellites, and some of them had a mission to do climate change. So they are also practically free, like planet data. So the writing on the right-hand side is that scientific satellite, the problem is that it's not very easy that you could process it, but usually you have new technology. So that puts a constraint on whether you could use some of these satellite off the line and even for real-time monitoring, but that's what's needed. All right, so just a very brief, more in detail. So I want to try to highlight all the satellite we have been using, but not all the commercial satellite yet, because some of them cost us money. So ALOS, Sentinel-1, you know, is Japanese and European. And then the other two companies is Kepler, SAR, and they are all XRs, by the way, and ICE-I. So this is the European commercial satellites, and some of these satellite companies are springing up. And then many of you probably are familiar with the Planet Dove, which is the original type of satellites, and then they added these Super Dove, which is much higher resolution, and then SkySat. These are stereo, but these are data are not for free. You have to buy it and so on. Anyway, let me fully, and then don't forget gravimetry is radar, but however, it's also what we consider remote sensing. So online over here, it's a very broad term, right? ISPRS is photogrammetry, and they are really, really good, but everyone else should use all the data for their own science and applications. All right, so this is a brief introduction for global navigation satellite system. I will try to skip over, and my apologies for all these quick. So on the left side, on the right side, sorry, top, you have all the agencies. Of course, the United States is the one that started GPS. Every other nations want their own system, primarily because of potential, like defensive purposes, national sovereignty, disaster, and so on. For example, the Japanese satellite, they would home in on Japan or vicinities. So not only cover globally, but the rest of the constellations will be covering. I think India, I'm not very familiar, maybe regional as well, but most probably global. All right, but the significant thing is that innovative measurements using GPS is just being invented day by day. And then I will be touching upon the reflectometry, the so-called reflectometry, or the interferometry, both on land and over in space. And I basically want to mention this 2019 in the document. It's debatable whether it has $1 billion a day in the US, or actually I think this is accurate, maybe even underestimated. So if you take this satellite offline, everybody will be in chaos in the world. All right, so so this is the only slide I have, and it's kind of very combining into one. So I apologize for the sort of very quick overview. So I'm just trying to show reviews. And this technology down there is called differential INSAR. Basically, you just to take SAR, whatever their frequency is, C-band, X-band that I mentioned before, and also L-band. So 3 different. So for example, in this case here is our work. So basically, we do interferogram, the so-called interferogram in Sentinel-1A. Coastal Louisiana. Actually, I apologize. This is not our work, but it's a former postdoc, Jin-Woo Kim at SMU, Southern Methodist University in Dallas, Texas, USA. So basically, they try to look at the subsidence. Actually, people make subsidence sometimes. And this other technique is called multi-temporal INSAR. It's basically so a lot of acronyms. I'm sorry, so it's not really, you could see the details, whatever they have at the bottom. What is TCP INSAR, temporal coherence? Basically, these technologies developed by the scientists, the engineers to do time series. So we are, so you could see Dr. Yuan Jia is in our group. So basically, try to, so on the right hand side is actually this is Bangladesh coastal polders, which is like levees. And then the levees is sinking. Basically, they try to look at all the changes. So in the red, you could see that it's actually sediment, the river sediment piling up. And this other color in the blue is subsidence. The subsidence actually could be very big. Well, actually, about 20 millimeter per year, 2 centimeters. On the right-hand side here, this is a tremendous subsidence, also done by Yuan Jia. So in Lost Hills, California, and you could see the red is subsidence. So the color scale sometimes is changing. And then this is her work also, Yuan's work on Tibetan Plateau. So they have a railway, so you could see the line. So it's sitting on sporadic permafrost, not permanent permafrost. So it's basically the terminology of active layer thickening is basically permafrost degrade and become water, so it's active. So the thickness, the terminology basically say if your thickness is thickening, meaning that you have more water, it's sort of opposite. So INSAR is to monitor all the deformations because so basically other places in Alaska, Siberia, many other places, Northern Europe also had this problem. Basically, the climate change is degrading permafrost. At the center now is a very technical and very useful, I would say, example applications is my friend and colleague, Professor Lei Zhang, now at Tongji University in China. So he was monitoring like airport in Hong Kong. He also did it in Melbourne, in the city, basically using XR to see the deformation. So this is arguably inexpensive cost, but however, you haven't figured out the launch of the satellites and everything. If data available to us is free, then it is very efficient. All right, so I have one example, maybe 2. If I have 2, I will skip it. So this is the work done by a student, former student, Teng Yi Yang. So we wanted to test whether the planet actually has daily sample flood monitoring anywhere in the world, right? In this case, that we prove that they do, because some of the flood, so this flood over here actually happens over a time of 6 days, whatever. There are floods actually 1 or 2 days. I'm not showing it over here, but we actually say that depending on your luck, sometimes you can actually monitor all these floods. So this is a case in Tanzania in April 2018. So this is a city in Kanadoni. So it's kind of sort of confusing here. B4 is on the right hand side. So you look at sort of the B4, and so there's no flood. The color code is a little bit not really clear. So you could see that after the flood appears, and more is the flood area. And then we could see, so this is like very small flood, relatively speaking. And then Sentinel-1 will have some problems. So this is like 3 to 5 meter resolution. Therefore, we could really see it. Oh, I also have this other flood in India. So let me just like quickly go through it. What's interesting to us is that when we did this work with a colleague who's interested in like solar energy, so he's an entrepreneur from India. So he showed us this case here. You could see all the solar panels over here on the ground, because he told me that they picked this area because it's never been a flood before, like very dry, so it's very safe. But then the flood came. You could look at the left side. I mean, this is a huge flood, right? So obviously damage all the solar panels. So we could use the panel and then color coded. You could see these flooded areas. All right, so I have to move on. Oh, forest fire. So this is a case also for the forest fire, because it's sort of a smaller situation. So let me sort of move on quickly over here. So we could actually use the infrared images for the it's only 4 bands, by the way, for those of you who are familiar with RGB and infrared, near infrared. So we could identify very small areas that has forest fire and so on. All right, so let's move on. So this is a totally another different application. And what I would do is I try to home in a little bit and then sort of do it slightly quick over here. So this is like exaggerated. On the left is exaggerated plot. So you have a GPS receiver on land. So it's actually very small. Obviously, they gather all the satellites from whatever satellite they have, but the key is the reflected satellite, in this case over the ocean. And then the schematic you saw before, but you have to use a technique called interferometry is first actually developed by Christine Lawson. She's a retired professor from University of Colorado. So we highlight a case in Lake Huron in the Great Lakes, nearby Columbus, Ohio over here. So you could actually compare this data with GPS. So here's the comparison. The RMS difference is very small because we average. So one is GPS, one is tide gauge. But there are some differences, and I don't want to go into it. But this is a signal opportunity. In other words, we get some kind of measurement that we don't expect it to be, but it could be used for, in this case, lake monitoring or ocean monitoring. So then this topic is very quickly, I may probably pass over. So many cases. This is the Atlantic hurricane, North America, we call it hurricanes. India, we call it cyclone, and typhoon in Southeast Asia. So they are all the same. They are very ASC induced, very devastating to human. So you could see we try to highlight that we could actually use the in situ SNR GPS reflectometry data. So these acronyms are GPS stations. And so I'm gonna show, so there are actually 4 stations. So on the left, you could see in Louisiana, Texas, and so on. So this is Louisiana. We're gonna show in this case here. It actually sits on a continental shelf, about 200 100 meters away. So basically you have a very high pulse. You could see the ocean sort of much better than just a GPS sitting on land. All right, so I wanted to just highlight this case. So these are the instruments. So this plot on the left is we try to compare the sea level measure by this GNSSR and the tide gauge, because tide gauge actually does not have vertical information. GPS, however, it has vertical information. So you see the correlations around 0.97. So it's very accurate, but there's some, there's some details that they don't agree, but I will skip the technical details. So I want to show this one case over here. So actually this is the Louisiana case. So on your left side is the sea level. The sea level, there are two sea levels. One is called GPS, is sort of red, if you could see. And then the tide gauge sitting on the platform. So it is blue. So it sort of covers. And then there's wind speed, because there's instrument on the top, right? So the wind speed is underneath. So you could sort of correlate sometimes the wind speed with the wave sea level go up. So this is a collection of all the hurricanes that pass through. We could identify. For example, Laura is a devastating hurricane, tropical storm, and so on. So this is something. So obviously, if you already have tide gauge, you can actually measure it, right? But I'm talking about it where there's no tide gauge, but you have GPS, you have some free data. Right, let me move on. So the next thing is the satellite that's already, so 8QSat is still operating. It's a very inexpensive satellite. It's called QSat. So you could see the over here, this is the so-called Cyclone GNSS. It's only in the equatorial region, so they take the reflections. But their purpose is get wind speed, because the instrument on board is not very accurate. It's only single frequency because of the cost and algorithm. So what we're gonna do is that actually stretch a little bit further. It's not designed by the mission to do the so-called satellite altimetry. So I have two examples. So this satellite also say get signals over a lake called Nankou Lake over Tibetan Plateau in China. So basically, this is the regular altimeter, and the blue is actually the tide gauge. So this is the ground truth, right? So we're gonna look at using signals, basically a processing, and then so this is a case where we actually develop methodology. We could, so a blowout case over here. So this is the reflected signal, which is in red. You could see the dots over here. Again, this is not designed to do precise altimetry at all. There are orbit errors, many other errors. So I'm sorry for the lack of technical discussion, but this is a sort of nice case scenario because it's over the lake. If it's over the ocean, a lot of times it's not coherent, that you cannot use in the interferometry, so you don't really get these kind of nice results. All right. So the other thing I want to highlight would be the commercial satellites. I know people, including us, is really try to do the work on the reflectometry height. So these satellites are originally designed for atmosphere, for radio occultation, which I did not cover over here. All right, let's move on. So now we turn to satellite altimetry. What the concept is very simple, but the detail is very complicated. Is that so laser or radar emits the radar from the satellite and bounces off water, actually land and so on. And then you get it. So this is very accurate, roughly about a couple centimeters, including all the errors. So for example, we have a project in India. We actually make all these points over static. So just like a virtual tide gauge. And then we could, for example, have about 10 years, 20 years of time series of each of these points. So over 10 and over 2 cases of different wafers with different different wafers with different altimeter satellites. Again, the time series combined is about 30 years. And this product would eventually be making available. So people just like hopefully could monitor the data and then just get wafer gauges, just like wafer gauges. All right, so this over here is an application that's not exactly very popular. It was actually done by our group, which is try to measure the deformation over land, which the radar altimeter is definitely not designed to do. So it's kind of complicated. So Central Valley, I'm going to showcase just Central Valley, California. It is one of the world's
Could you hear me?
It looked like we are disconnected to Dr. Su.
Okay, we'll wait for a minute. Maybe he'll join.
Yeah, maybe let's wait. There might be some technical glitch
Maybe
at his side.
he'll join. Sure.
I'm
Yes,
sorry for
let's
this.
let's wait for him for 1 or 2 minutes.
Yeah, sure. In the meantime, you can put your questions on chat box or Q&A. And also, we have put some links there regarding the information about different midterm symposiums and travel grants available. We'll put that link again for those who joined later for the webinar. So there are several travel grants available to participate in those midterm symposiums. Feel free to give it a check. Yeah, he's back now.
Oh, it says unable. Can you start my video, please?
You can start it, Dr. Su.
Yeah, please go ahead. Start sharing the screen.
Yeah, I apologize. Somebody's tripped over my power line outside. Let me see. Let me restart it.
Maybe you can share your screen.
Yes, share my screen.
Great. Yeah.
So my apologies. So again, so we try to highlight some radar altimeter deformation over land. So just the results over here, for example, using this satellite called CryoSat-2, we could actually map the deformation over here. And the deformation is huge. It's like 40 millimeter per year. 40 centimeter per year because of land sinking. And over here this is sort of the trended time series you could see on the right-hand side. And then in green is a GPS, but they are not really measuring the same thing on the land. So altimeters on your in blue. So what's happening? So you could see the tracks laying over, and this is the point actually over at Curriculum. At GPS stations about 10 kilometers away. So we're comparing maybe slightly off. But what's interesting I wanted to show is that, so this is the altimeter observed deformation. So it's sort of coincident with something like when a storm coming, when a flood is the 2017 Northern California flood in the US, the land will actually go up because the water went down into the aquifer and the land actually rises up. And afterwards, when the storm is subside, all the water went away, and then the land come back again. This is work in progress. We have not exactly figured out everything and publishing it. All right, so the other application is this so-called lake meteoroid tsunami. So this is like a hurricane over lakes. So I want to show you, just scale over, show you an animation. So this is, we use radar altimeter. We actually have to use machine learning to combine the water level gauges. You could see that the evolution of some of these meteoroid tsunami, because they propagate very fast. So Lake Erie is part of the Great Lakes. It's not going to be very large, but it propagates. For example, you could see 2021 December, and so some of these storms are not really detected, but actually it happened. So this is one case I wanted to show, say up to December 11 or 12, it is going to be showing up on the right-hand side. You have to wait a little bit. So in fact, if this kind of a signal could be a monitoring system, it could have early warning and so on, hopefully. So, but this is simply a scientific experiment, is like observing. We're not doing anything like potential predicting. You could see that December 11 is actually huge, but you could see it's actually at the nighttime, sort of. I think this is Eastern Standard Time, and so no one really, detected it. So the next and the last topic is this satellite called that I mentioned before, the gravity recovery and climate experiment. I apologize for the equations not intended. It's one satellite chasing the other, like you see over here. And we actually, the precise distance, so the accuracy for the gray satellite is about a micron, which is 10 to the minus 9 meters relative distance. You monitor that, you monitor the gravity underneath the Earth when something changes. So that's the idea. So I want to show like two examples. One is the satellite could actually be, so this is a continent over almost the India and Himalayas. So these two big regions are actually the equatorial region within India. So I'm showing on the right-hand side is basically, apologize for all the acronyms. So it's basically, the red is the satellite data, and never mind the model. So basically, we could theoretically estimate the groundwater storage in these regions. So these are three different river basins. You could see that it's declining, and sometimes it could be abruptly declining, but this is an anthropogenic effect. All right, so this other example is basically flood. So this is a long time series. We will try to highlight the 2021 flood using the follow-on. So let me, let me forward it. So let's, because we started in 2019 for take the whole picture. This could be already sort of operational. We process the GRACE data in a different way. So here is so 2021. So this is the July and to August 2021 flood in India. So it's Maharashtra flood. You could see that it's on the left. So it's actually 300 casualties. It's very large flood. And the other one we wanted to highlight is the Pakistan flood. Actually, and this is due to the monsoon persisting. This is a huge flood that spans over almost a year, like in Pakistan. So it's causing a lot of damages. I think if you allow me, there's one other example. I will scale over the sort of the complicated so-called deep learning, physics-based deep learning. So what we wanted to do is to downscale the satellite gravimetry data and actually try to see whether we could see the hurricane landing. For example, in the one is called Harvey. Harvey is it looks over basically Houston. And then you could see on land this huge red is just inundation of flood. due to the hurricane. And this will be the last, this will be the last slide over here, the last slide. So this is the LoRa that you saw. Actually, we use GPS reflectometry to try to track the ocean side of the hurricane signal. So let's see. So the hurricane is coming. This is a relatively smaller signal, so you could see that it went land on Louisiana, go into inland. Actually, it went all the way to New York. You could see the residual, basically rain and inundation or the flood. Yeah, thank you very much. I apologize for the disruption.
Thank you, Shum. I think we had a quick glance of the satellite geodesy, starting with some of the applications related to INSAR, remote sensing platforms, CubeSats, etc. I think the important aspects are primarily is this 2020 Atlantic hurricane data of the 4 stations in Louisiana, etc. is quite interesting. And the most interesting aspect of the presentation is the coverage of the radar altimetric altimeter data in terms of the sensing of the land subsidence using the cryosat. The other one is the most important aspect I consider is the Indian example of radar altimetric data use it for generation of the virtual water level in entire dams, over the dams, lakes, etc., with specific focus around Krishna River. It's very interesting. And one of the most important aspects which he mentioned is the utilization of the PlanetScope, which has got a resolution of about approximately 3 meters. And the PlanetScope operated by Planet Company, a constellation of about, if I remember correctly, more than 125 satellites able to image the entire land surface of the Earth every day. That is one of the unique combinations of the PlanetScope, which provides excellent data in the real-time mode. The examples presented by Dr. Shum are very unique and meet the requirements, and I submit to the younger community here to take up these imagery for data processing and applications to related to the climate change and disaster risk reduction, etc. Thank you, Shum, for your wonderful presentation. Kindly stay back. If there are any questions, we'll come back to you kindly. So thank you, Shum.
Thank you very much.
Yeah. So if you permit, we'll go to the next speaker.
Sure.
Is Dr. Dayasagar. Dr. Dayasagar is a professor of Indian Statistical Institute, head at Bangalore Center in India. And he is a IEEE GRSS distinguished lecturer during 2020-22 and the founding chairman of the Bangalore section of the IEEE GRSS chapter. Dr. Dayasagar was elected as a member of the New York Academy of Sciences and also a fellow of the Royal Geographic Society and as a senior member of the IEEE Geoscience and Remote Sensing Society. For most of the time, he was involved in various aspects related to mathematical morphology. And I'm watching Dr. Dayasagar for almost the last 20-25 years and is an excellent researcher, contributing significantly to the various aspects of the mathematical morphology and with a specific general focus in the area of the geostatistics. In fact, geostatistics is a class of the statistics used to analyze and also predict the values associated with the what you call as the spatial phenomena, if I remember correctly. And the geostatistics incorporates both spatial as well as the temporal coordinates of the data when you are trying to analyze. And is wonderful domain which has got excellent scope. And today he is going to talk to us on a very important topic on mathematical morphology in digital elevation models. Dr. Dayasagar, please.
Thank you, Professor Murali Krishna, sir. It's a great to have your invitation. And I'll share my slides and then I'll see that whether I can show what I wanted to show within a span of 30 minutes. Sorry, this is not the one. No, not this one. Sorry. Sorry, and just take. Yes. Yeah, sorry for taking a bit longer time. Yeah, hope you are able to see the slides.
You are able to see.
Yeah, so there are two things here, and one is the phrase mathematical morphology, and other one is digital elevation models. And as I could see, the many of the audience, young audience, they are all quite familiar with digital elevation models, and perhaps they are not very colorful images, but digital elevation models have a lot of geometric, morphologic, and topologic information. And with our naked eye, and we can feel that it provides a lot of geometric information, but how to unravel those things? And one of the mathematical fields that I have thoroughly enjoyed for the last 3 decades is mathematical morphology. It is a simple set theoretic based mathematics to study the shapes and functions. And to give a simple example, like mathematical morphology is a technique and a theory to study the geometric structures based on lattice theory, set theory, topology, and random functions. And the idea of this particular webinar is to popularize two things. One is, of course, digital elevation models. And I feel that billions of dollars have been spent on, generation of the whole technology to generate digital elevation models from various different remotely sensed data, and also the simple surveyed topographic maps. And I'll come back to that point and how accurate are these DEMs. And so many people used to ask, and how accurate are the morphology-based algorithm that I have developed over a period of 3 decades. And I used to tell that the moment you provide me a digital elevation model, very accurate, and then the results that we derive through these morphology-based spatial algorithms are very, very accurate. So before getting into the details, and so I'm so grateful to Professor I.V. Murali Krishna and Professor Laurent Polidori and Dr. Lakshmi Thapa and ISPRS in general to give me this opportunity to just showcase my work within a short span of time. And so this is the same title, Mathematical Morphology and Digital Elevation Models, is also a book that is to come out perhaps by end of this year. And so that is under a signal processing book series of image processing and analysis of Earth observation data by Taylor and Francis Publishers. And so it's a bit verbose, but this particular slide. But when we talk about some scientific outcomes out of the data that we have been working on, that is digital elevation models. And when you derive something about a phenomenon or a process, and if we can really talk about the spatiotemporal behavior of a particular phenomenon, let us say the floods that very nicely Professor Shum has shown that. So can we really talk about the whole episodic behavior, the before the flood and exactly at the flood, and then after the flood, and how this flood water has been spreading over the geographical space, and how it is getting receding, And all that, if we can really model it, and so that is what I say, that where we can really introduce some kind of nonlinear physics, nonlinear dynamics to understand the spatiotemporal dynamics of a specific phenomenon. Perhaps it is floods, or it may be dune dynamics. And one of the most interesting aspect for me is dune dynamics. And so very old book of Raphael Bagnold, and he has written a book on the physics of sand dunes. But with the enormous amount of data that we get for the desert dunes, and so can we really model those desert dunes, how they behave, and morphologically and geometrically and topologically. And so there is a lot of physics that we can really derive from those things. And then, so as I mentioned here, digital elevation model is an engineering marvel, an important source of data for geoscientists and planetary geoscientists, but it has been underutilized for various reasons. And I will show an opinions piece, that educational piece that I have written for IEEE Geoscience and Remote Sensing magazine, and where I have highlighted knowing a bit of geometry relevant mathematics would really help the researchers to unravel geometric, morphologic, and topologic information from digital elevation models. And so that is the mathematics. Like mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. And I still say, take this subject, a topic of mathematical morphology, to heart, and then learn to think morphologically, and then you will really do wonders with whatever the data that you really consider. And in mathematical morphology, data will be seen everything as a relief. And whether you are taking a color image or grayscale image, and the higher the grayscale value, higher the elevation. So instead of taking such kind of pseudo images, and I straight away take the images digital elevation models, where each grayscale value will tell us a normalized elevation value. So for instance, in the peak of Himalayas is shown it as a 255 grayscale value, as long as we depict digital elevation model in terms of 8 bits per pixel. And then the least value will be shown it as a dark pixel, and which is a topographically depressed zone. So in morphology, as it is mentioned here, data, I would say it is a f of xy, which is a simple spatial function at grayscale values or elevation values at xy spatial position, is investigated with respect to another data that is called B, or the structuring element or a structuring function from the terms of mathematical morphology, with certain characteristic information. It is like data is being investigated with another data, but that another data is a structuring function or a structuring element which has certain characteristic information. And by tuning the characteristic information according to the user's requirements, and you can unravel many features. Some of those features probably you can have a look at in the next slide. And so this is to show that in geospatial data sciences, I say the basic ingredients are information retrieval, information characterization, information reasoning, and modeling, simulation, and visualization. All these are basic ingredients whenever you talk about the spatial data science. Just quickly to show you, and these panels, like you have a synthetic digital elevation model, and what are the two very important topological quantities that you can really derive are nothing but river network and ridge connectivity network. And those river and ridge connectivity networks, we have many commercial softwares, and they provide very nice connected features. But when you really look at rather gently sloped area, like probably the tidal regions, if you have a digital elevation model in tidal regions, many of those commercial softwares will fail to provide you the actual valley connectivity networks there. But how we have addressed that with mathematical morphology, and I will show you in the subsequent slides. And then how to partition a given digital elevation model into watersheds, sub-watersheds in a hierarchical manner. And so that is another case study. And this is one case study I would like to show you in the subsequent slides. And once you have a digital elevation model, perhaps you can convert that into a kind of hill slope region and no hill slope region. It is typically the moment you subtract the skeleton for the terrestrial surface is a river network. The moment you subtract the skeletal network and whatever is left over is perhaps the hill slope region. And rather than going for studying the terrestrial surface and characterizing the terrestrial surface in terms of river network, we have a very established classical geomorphological studies. I think some of the audience, and I could see Professor Raghavaswamy is there in the audience, and he has done a lot of work on morphometry and all that. And by excluding the river morphometry and how to actually study the hill slope regions, and we have a way to handle that by following a morphologically shaped decomposed techniques, and that also I will show it. And then further, we can also generate within a watershed a kind of landscape. And so a host of various different topological conditions you can impose, and then you can generate kind of landscapes. And so one of the studies is that how to artificially generate a landscape within a watershed. And you can see that this is a river network, and this is a typical synthetic digital elevation model. And then the landscapes that we have generated by showing some kind of vertical exaggerations here. So that is another case study. And then roughness quantification is so important because of late I have read a nice paper which was published in Geophysical Research Letters, and the roughness and the number of aftershocks are very nicely linked by a group of researchers. And so many a times, and after the earthquakes, there will be so many aftershocks, and those aftershocks number is in large number when the terrestrial surface is so complex. So how to quantify that? And the complexity is not just the global complexity. So a host of a spectrum of roughness values, how to really compute. And we have a way to compute that by using some kind of morphological granulometries. It is like a multi-scaling of the given data, and you can actually transform the given digital elevation model in terms of morphological openings, multi-scale morphological openings, which is nothing but the granulometric analysis. And then you can see how that particular digital elevation model within a watershed boundary is losing its energy, and then how the loss of energy is from one cycle to another cycle of opening transformation is not uniform. That tells about the roughness with respect to the B that we have chosen, because it is not just the scale. We have spent a lot of time understanding the spatial scale-based analysis, but it is not just the scale, and it is also the shape is very important to quantify any terrestrial surface. So you will see that we get some kind of scale invariant measures, but they are all shape dependent. At the end, it is not just the scale, it is about the shape matters. And that study is another study here. And so that is also extended to compute a host of a spectrum of roughness values, because from left to right, when you see a particular watershed, you have one particular roughness value. From diagonally from northwestern side to the southeastern side, and if you perform some kind of granulometric analysis, and you get a different kind of roughness values. In turn, and we get the directional roughness values, a host of directional roughness values, and we can tell that in which particular direction, and the watershed is very vulnerable to any kind of perturbations. Perturbations may come from two sides. One is tectonic activity, the other one is endogenic activity, that is weather-related disturbances. So that is another case study, we will show it, and then probably if time permits, and I will show how. I have seen Professor Shum has shown very nice pictures, and so desert regions, and so if you have a digital elevation model, because in desert regions, and you will see the dune surfaces are very time varying across, within days, and you see the dune surfaces will change. And so can we derive some kind of scientific outcomes of those things? Because we also have a restriction that we cannot get the data in a real-time continuum mode. And when you have snapshot like digital elevation models at probably in a span of 1 month intervals, And can we really convert that sparse digital elevation model data to near continuum data? So which requires a hierarchical interpolations, computations of the hierarchical interpolations, and you can see it, this is the source data, this is the target data. Between these two and whatever we have computed by following some morphological medians is this particular data. Perhaps if the gap between these two is 30 days, and perhaps this is after 15th day, and then between source and the median, and then you can compute another median. Between the median and the target, you can compute another median. This is a hierarchical process until there is no further scope for you to put one more interpolation, and then you can generate it, and then you can show it. A sparse discrete data has been converted into continuum form. And so just to give you an overview, the digital elevation models, you have already had something about, I see them as the spatial fields, but the variable there is the elevation, which is changing from one spatial position to another spatial position. The mathematical morphology, notations, equations, and transformations. And as I mentioned, and so I will probably skip all the equations because this entire topic, I used to give about 26 lectures for a doctoral student. It's a 3-credit course, but I don't really want to go, but I'll direct the audience to look at some of the YouTube lectures that I have given through NPTEL style at the end of the talk. And then spatial morphological algorithms based on so many things. And so out of several spatial algorithms, probably I would like to highlight, I have already shown some in one single slide, and unique network extraction from DEMs and DEM partitions via morphological skeletonization. It's a wonderful transformation, which is very popular in coding techniques in computer science. And so given a data, and then so you can follow some kind of Huffman coding, Elias coding, and then you transmit the data, and then by knowing what kind of coding that you have followed, you can also retrieve the original things, because you cannot send the whole data in whichever way it is available. You can convert that into simple code so that you can reduce its memory, storage memory, and then you transmit it, and then you reconstruct it. The same principle is involved here. Given any shape or any function, you can convert that into a skeletal form. The skeleton is nothing but 1 pixel wide caricature that summarizes overall shape, size, and the structure and orientation of the given object or a spatial field. And typically the skeleton of a digital elevation model is nothing but the valley connectivity network, which is a river network. And then what are the simple equation that we followed, and I'll show it. And then the next case is about derivation of scale invariant but shape dependent power loss by using shape decompositions. When you remove the skeleton from the body, and whatever is left over, in physical terms, it is called as fat fractal. And typically on terrestrial sciences, and when you remove the river network from the terrestrial surface, whatever you see is a hill slope region. Can we really pack that hill slope region with some kind of shapes in a non-overlapping way, eventually to derive a power law, and which is not just the scale invariant, but it is shape dependent? That also you will see it. And the superficial roughness quantification via granulometry, it is nothing but looking at something at different magnifications, because we don't take the picture of a particular terrestrial surface at different magnifications, but we can always simulate that process of seeing that particular one at a multiple spatial scales by following multi-scale morphological openings in a cyclic form. And then we can make the coarse resolution images still coarser, or fine resolution DEMs to the coarser scales. And that is done not in a linear fashion, but that is done with a non-linear fashion, which is the advantage to quantify the roughness values, which are also called morphological entropies. And the morphing of source DEM into DEM and transforming sparse DEM into dense DEMs. And these are typically the morphological interpolations. And this classification spatial optimization, I'll skip because I don't think there will be enough time to do that. So this is the opinion education piece. As I mentioned, digital elevation models, an important source of data for geoscientists, which I have written for IEEE Geoscience and Remote Sensing magazine a few years ago. And so what is highlighted here, knowing a specific mathematics, for me, and I feel that digital mathematical morphology is a wonderful field which has a lot of adaptability, and then which can, if you are intuitive and you can handle all ingredients of the spatial data science. And similarly, you have wavelet theory, you have fuzzy set theory, rough set theory, and discrete mathematics. And knowing one of those mathematical fields would really help you looking at digital elevation models in an entirely different way, and then we can derive a lot of scientific outcomes. And I'm sure that the people of the audience are quite familiar with digital elevation models. And so these are different digital elevation models, and Cartosart DEM, a synthetic DEM, and Topsart DEM. And then, so we also have SRTM DEM. And then this is the bathymetry of San Francisco Bay. And then, so from topographic map, from simple contours, we have generated DEM. And I still believe that because there are certain uncertainties on the DEMs which are derived from remotely sensed data, and we tried with a simple elevation contours traced from the topographic map, and then with very sparse contours, but we have made them into denser digital elevation models, which is worth trying. And so though it is time consuming, and we have a large number of various different digital elevation models, Venus DEMs, Mars DEMs, and I was so much thrilled to see this Chandrayaan 2 optical high resolution camera based digital elevation model, which is with 25 centimeter resolution, and we can really do wonders with that. So I mentioned here spatial data and relevant mathematics and science outcome of out of the spatial data and spatial information. And these are some of the geometric, morphological, topologic quantities and large number of things. And I think many of you are geoscientists, and they are all very familiar with these scientific outcomes that one can derive it. So as I mentioned, once you have accurate DEM, and then knowing one of the good mathematical fields would really help you people. And then mathematical morphology, and these two Frenchmen have really done great things by inventing the mathematical morphology. And then you have binary mathematical morphology, grayscale morphology, graph morphology, and adaptive mathematical morphology. Those who want to really venture into mathematical morphological research, I really suggest graph morphology and adaptive mathematical morphology. There are many, many open challenges. But as I mentioned, morphological skeletonization, morphological shape decomposition, granulometries, morphological distances, and morphological interpolations, how they helped me publishing so many papers just by applying mathematical morphology and DEMs, and we have published a bunch of papers in IEEE transactions. I would skip, but before just going to the next slide, and there are 4 fundamental morphological operations: erosion to shrink, dilation to expand, opening to smoothen from inside, and closing to smoothen from outside. Mind you, all these 4 morphological operations are nonlinear operations. Because of their nonlinearity properties, and we could get many, many advantages when we are trying to, tease the data, such as digital elevation models. It has a number of applications in hyperspectral remote sensing classification, and they have called it as, instead of calling as granulometries, that particular group, they've termed it as a kind of morphological profiles, extended morphological profiles, and attribute profiles. And they are typically the granulometric analysis, which is nothing else. And so those are some of the things, like, are we dealing with the data which is in a binary form? Perhaps what is binary form from digital elevation model? When you threshold elevation, when you perform a kind of thresholding, and so whatever you get is a thresholded elevation region. And so do you want to work on that black and white image? And you have binary morphological operations. You want to directly work on the grayscale digital elevation models, you have grayscale morphological operations. And so those operations I will skip. And so erosion to shrink, dilation to expand. Erosion to shrink, that this is a grayscale, this is a function, this is a set. So dilation to expand, and dilation to add something more to the surface. And you have closing and openings, which are nothing but the cascade operations. When you perform erosion followed by dilation, and you are smoothing something from inside. When you are performing dilation followed by erosion, you are smoothing something from the outside. And you just imagine you are rolling a ball from outside of a particular object and inside from the particular object, to which are all the regions that particular ball will reach. and to which are all the regions that it cannot reach. And so these are the two things will get you the two topological quantities there. Elevation, the connectivity networks. You can see this. This is a kind of digital elevation model. By following a simple skeletonization where you have erosion and the opening by arbitrary size structuring elements, and you can take all skeletal subsets that you derive from this particular expression and take the union of that, and you get a river network like this. And then you invert the DEM and perform the similar skeletonization operation, and you get the ridge connectivity network things. And so these are the things that we have shown here, a digital elevation model. All green lines are valley connectivity networks, blue lines are ridge connectivity networks. And then their partitions into the hierarchically partitioned watersheds are shown here. And here also we followed a kind of weighted skeletonization by influence zones. You have multiple regional minima and use them as the water bodies and allow those water bodies to flood with different speeds. And then where that floodwater front lines will extinguish each other, you construct a dam. That is a simple principle of watershed transformation in mathematical morphology. And using those ideas, we could also construct what is there within the boundary of a kind of fractal watershed. And then you have networks here, and then we can convert the inside, which is a planar feature here, the internal region we have converted into some kind of topologically relevant regions. And then that is where we could really convert the given simple fractal planar feature into a kind of a landscape here. And then I was talking about morphological shape decomposite based terrestrial components derivation. So that is on the hill slope region, and it stems from this is a Napoleon space, and you can pack that with whatever the shape that you take. And this is the B that I have taken, an octagon as a B. And then by following the morphological shape decomposition, I could pack this particular Apollonian space such that there is no void space at the end. And you can see larger gons here and smaller gons here, and then it follows a kind of power law relationship. You have a fractal with different shapes. I have packed it. This is with a square, this is with a rhombus, this is with an octagon, and you can see those interfaces here. So how we have applied this, you look at this, and many geomorphometricians think that these three networks are topologically invariant because those three networks would get you the same morphometric quantities like bifurcation ratio, mean length ratio, and then mean area ratios. And in turn, they yield the same order ratios, and in turn, the same fractal dimensions. If you can really subtract this from its corresponding basin boundary, that is what we have done it here. And so this network is removed from its basin outline. And then this white space is the hill slope region. And we started packing that hill slope region by following the morphological shape decomposition. And then we derived some power law relationships like the size of the object versus how many number of such objects are there in the packed region. And so that has given us a power law relationship, which is scale invariant, but shape dependent. The moment you change the shape from octagon to square, you get a different power law relationship. And the moment you change that square to a triangle, you get a different power law relationship. So that is where I think the quantitative geomorphologists, they really appreciate it is not just the scale invariant based power laws that we derive, but it is also dependent on the shapes. So these are some of the results. And then the next level is the granulometric analysis. And what we do is we perform erosion followed by dilation to different cycles. And you can see it at the cycle 1, erosion followed by cycle 1 dilation would show a digital elevation model like this. After 40 cycles of erosion followed by 40 cycles of dilations, so it is actually becoming darkened and darkened and darkened and darkened. So it is actually losing its information, energy it is losing. That loss of information is completely in a converse way when you perform dilation followed by erosions, which is called as a closing operation. One dilation followed by one erosion, 40 cycles of dilations followed by 40 cycles of erosion, and then how it has gained the information, and you could see it here. So the loss of information, we compute it here, and so a set of equations, and I don't go completely into this. So there are two major parameters in this particular equation. One is the pattern spectrum, which is there on this numerator side, and this is the total energy of the function here. And then that particular ratio will give you a probability like quantity. And then for different sizes of the B that we use, with different cycles, it is increasing. The size of B, the structuring element, is increasing. And then we can at the end compute a kind of parameter called uncertainty index, which is also called morphological entropy or granulometric index. The higher the value, the higher the roughness. But those roughness values, if you are computing with B, which is a kind of symmetric, and you get a global roughness value. If they are at a different different directions, and you see that those are directional structuring elements. And so this particular lower Indus Basin area partitioned into 31 watersheds, and their vertical exaggeration, you can see it here, 3D thing. And then they're classified based on the directional roughness values that we have computed by following a different directional structuring elements here. You can see it. This is a compact symmetric structuring element, but these are with a different directions. So this is with northeast to southwest, and sorry, the northeast to southwest, and this is northwest to southeast, and so this is north south, and this is east west. And so 4 different directions we have used. And if you are intuitive and you can use higher directional structuring elements also, you can see how a digital elevation model is behaving when you are performing the different cycles of openings and closings by changing the structuring element characteristics. And all that were shown here, but this is a nice paper. One can see it in IEEE JSTARS for more details. So I think I can take another 4 or 5 minutes, sir.
Please take 5 minutes.
Yeah, 5 minutes, yes. So the morphological median, which is nothing but, you see here, there are some sparse contours here. This was done by my recent PhD student. She has published this in IEEE TGRS, Geetika Burman. So this is a sparse contours, and how to make this into dense contours. And somehow you have to insert another contour between the successive contours, because assuming that you don't have that particular dense data, and then you have very sparse contour data. And this is very obvious when we are looking at a topographic map with 1:250 scale and 1:50,000 scale, and you see that 50,000 scale will have contours with more dense. And then can we simulate the whole process? And then we typically followed hierarchical computations of morphological medians between the successive contours. So what we do, and so we take all thresholded elevation regions, xt versus xt plus 1 successive contours, take the intersection of those two things, and then take the union of those two things, and dilate it to the lambda levels ranging from 0 to some capital N, and then union you have to erode it, and then you can actually compute the medial line between the two successive contours. Why it should be at the median level? It can be even at the weighted median levels. By tuning this B parameter, and you can make it in more realistic, close to the reality. So that is one aspect. That case study we have shown it here. The other case study is when we are working on the digital elevation models, and they are not just black and white like this, and they are like grayscale surfaces. And so how to compute the morphological median is nothing but take the infima of these source and target DEMs, and infima is nothing but the pointwise minimum at the specific locations, and pointwise maximum is the suprema, and infima you dilate it, and suprema you erode it, and do it for all n values, and take the suprema of all those the median element that you are computing. You can compute this, the interpolated thing. So this is one interpolation you got from the source to target, and you can make it hierarchical way, that this to this and this to this, and you can generate another 2 interpolations. This is a hierarchical process in 2 power n form, and you can generate all possible interpolations between given source and target DEMs, right? So this is what is shown in a kind of exaggerated way. So these are the hierarchical interpolations that we generated, and then put them in a sequence. You run it, and then initially you have only 2 DEMs. probably so the day 1 and day 30th day. And so you have generated in between days and what should have been the DEMs. And when you don't have a specific mechanism to get the DEMs in a real-time mode, and so these morphological medians would really help us. This is an algorithm that we have shown it. So this is again some kind of animation that we have shown. And these are animations with the different structuring elements, how source DEM is becoming, as a target DEM. And so this is another with a different 4 connectivity structuring elements and 8 connectivity structuring element. So with simple rhombical type of structuring element, the kind of transition that we got from source to target is very smooth and then close to the reality. And I will probably take one more. This is the last slide. Probably the conclusion is, with all these spatial algorithms, would we be in a position to better understand spatiotemporal behavior of terrestrial phenomena and dynamical behavior of terrestrial process? This would be an open challenge. And the surfacial phenomena include numerous geomorphological features. Considering feature-specific attractors, this is the word that I have borrowed from nonlinear physics, to better understand the dynamical behaviors of each and every geomorphological feature is a challenge. But some of the things that we can really show a simple attractor, like how would sand dune behaves. So that can be, at least heuristically, I can say that can be easily modeled because we have data, we have the techniques, and then we can really generate a kind of attractor and which region is behaving in what way. And can we show a simple attractor like how an oscillating pendulum, it's corresponding when there is no friction and it goes back and forth, and its corresponding attractor is a limit cycle. When there is a friction and then it goes and it comes back to the rest state, and which is like a spiral and attracting to a fixed point. So these are the attractors. Can we derive such kind of attractors for geomorphological process and phenomena? So mathematical morphology, robust mathematical theory, the earth and planetary science communities need to pay more attention to deal with this type of challenge. And it's an area of geoscience that most people don't realize. So that we can really, the way we look at the earth and other planetary surfaces, it will give us an entirely different scenario and a new branch of probably the morphological sciences of involvement in geosciences. These are various different books we have written, and this book, probably most of the cases that I have shown are in mathematical morphology and geomorphology and geographic information science. So this is the encyclopedia we have edited recently, which is about 2 volumes of almost 1800 pages. And there are various several special issues that we edited. And then, yes. And any questions, and I would be very happy to answer. And the next slide is probably if those who want to really learn about mathematical morphology. And I would be very happy if some institutes and universities will introduce this as a kind of a 3-credit course, and then it can be really covered in a very nice way within just 28 or about 36 hours of lectures. And so these are the lectures I have given at IIT Kharagpur about almost a decade ago. So they have recorded them as in NPTEL style, and then those who want to really look at, and you can see those YouTube channels. And then these were like, on pen and paper I have explained, and it is easy to understand. I'm not a mathematician, but I could understand mathematical morphology. And I am sure that many of you can really take this subject to further levels. Thank you very much.
Thank you, Dr. Dayasagar. I think we all appreciate that mathematical morphology is a wonderful theory with
Yes.
plenty of adaptability, as I stated, with the 4 nonlinear operators like erosion, dilation, opening, and closing, and essentially. And one of the things he has mentioned, how the skeletonization of the DEM has led to delineation of river network is one of the most significant, I think, it's the highlights of what we could derive.
Correct.
Earth scientists, they're trying to interpret an image. I think
Correct.
I'm extremely grateful. And one of the challenges that has been mentioned by Dr. Dayasagar is the graph mathematical morphology and adaptive mathematical morphology to be taken as or they've been pursued in greater detail as research topics. And I appeal to the youngsters here, and also they can utilize the NPTEL series of presentations available. There's a very good rich source of knowledge that is available at the just click of a button. So please look into those issues. And the main objective of this webinar is to promote the topics and encourage the youngsters to go for research. Thank you, Dr. Dayasagar, for the wonderful presentation. And I take the permission from my president of the ISPRS Commission 3, Dr. Laurent. I think Dr. B.L. Dikshitlu, who is the outstanding scientist in Indian Space Research Organization and the former director of National Remote Sensing Center, a unit of Indian Space Research Organization, is available in the I think in the participant list. If he is available, I want Dr. B.L. Dikshitlu to tell one word if he is there.
Oh, it's great, sir, to have him. I didn't realize that he is there. He's my great guru.
Dr. B.L. Dikshitlu, are you there, sir? I saw him in the list. So I just thought if you, and Dr. Raghava Swami, the former director at the National Remote Sensing Agency, group director at one of the units of Indian Space Research Organization, is there. Dr. Raghava Swami, you can take a minute and just say.
I think we should allow him to talk, sir, Professor Dikshitlu.
Is there, Professor Dikshitlu?
He is there, and I think somebody should allow him to ask.
Yeah, both Dikshitlu is entering. Dr. Dikshitlu, please, you raise your hand also. Can I request Dr. Dikshitlu to just, for the introduction, for those people who are not familiar with the people, he is known to all the people who are in the remote sensing community all over the world. He is, as I was telling, he's one of the very senior directors from India, and the renowned scientist, outstanding scientist from Indian Space Research Organization. Can I request Dr. Dikshitlu to come just address for 2 minutes?
Yeah, he can speak. If you can see him in the panelist, he should be able to speak and turn on.
He's there. I could see his name. His name has come. So he has raised his hand. Dr. Dikshitlu.
Sir, can you unmute yourself, sir?
Dr. Dikshitlu, you have to unmute yourself. Or any message from him? Or just there are some questions in the before I'll we'll come back to you that for a minute. Just
Hello.
Yeah, Dr. Dikshitlu, please.
You see, I studied these things about 40 years back, and I see now that complete change and additions, you said about the latest morphological phenomena like graph morphology and how to interpolate between the contours. They are all completely new, and I don't know who is the second man next to Dayasagar who can talk on these matters. I simply adore his lecture, and it is a highly thought-provoking lecture. Thank you.
Thank you, sir.
Thank you. Dr. Raghaswamy, for a minute, do you have anything to say? Dr. Raghaswamy. Yeah, may I request Dr. Lakshmi, can you just help me identify the questions?
Yes, so I can read the question that Kingsley asked to Dr. Dayasagar.
Yeah, please.
Yeah,
so he says,
we will come back to Raghaswamy after a minute. Let the question be answered.
Yeah, good day, everyone. I'm Kingsley from Lagos, Nigeria, and my question is directed to Dr. C.K. Sum. It is directed to C.K. Sum. I'm an undergraduate, and one of my research interests is using INSAR in monitoring subsidence. The challenge I have, though, is that GNSS observations of most subsiding areas in my country are not available. My question is, can one completely rely on remote sensing data like Sentinel, GRACE, and the likes to get a reliable result? If not, how can this challenge be overcome?
Dr. Shum, you are there? Dr. Shum.
I think he's left.
Okay, maybe you please note this question. We'll get the answer by mail to him from him. Okay?
Yeah, so there is another question to Dr. Sum too by anonymous attendees asking about GNSS system.
That's
So
both
what
the
we can do is we can write his email here so that the one
Dr. Sandhu.
inquiring can directly communicate with him. Is that okay, Dr. Murali Krishna?
Please put the mail here, his email here, so that it will be conveyed directly by the people who question. They can send a question. I request the person from Nigeria to send the question by mail to Dr. Shum. Okay?
Thank you so much.
So, any questions, Dr. Dayasagar, please, in the meantime?
Yeah, there are remarkable notes to him saying it was good one. Thank you. Thank you. And also VR Murthy, he says, Dr. Sagar, Dr. Anki, and ISPRS in general. I'm elevated by participating in such a good studies presented by Dr. Sum and Dr. Sagar. I hope the DM and other altimetry data will also be used in addition to morphological studies applied to urban vertical growth monitoring, earthquake and polar glacier movements and tectonic movements. Excellent presentations and case studies. Thank you all. Yeah,
Yeah.
it's a kind of note. And yeah, there are some notes like thank you, Dr. Daya. What an enlightenment on skeletonization by Edegoki. Coyote Martins, if I pronounced the name correctly. Yeah, there are some other notes about happy to see and listen to Dr. Dayasagar on your passionate interest and in-depth study on dams, which are fundamental to morphological study. Yeah, there are several notes like this. Thank you, everyone.
Yeah, I think.
Yeah, not the explicit questions. There
Please
are.
put the mail here in the meantime to the person for
Yes.
the understanding. Both the mails you can put it to any questions are there, they can directly send to them. Okay? That
Yes,
will be.
sure.
In the meantime, can I ask for Dr. Raghava to address for a minute, please?
Yes, he should be able to talk.
Hello.
Yes, sir.
Is the director, a group director at Indian Spaces Organization Unit National Remote Sensing Center. Are you online, Dr. Raghava?
Yeah, are you able to hear?
Yeah, please go ahead. But take a minute and just say hello to her.
Okay. First of all, thank you, Dr. Murali Krishna. It was a very wonderful initiation taken by you. And I heard both the wonderful talks given by Dr. Shum and then my old, I could say, Dr. Dayasagar, my old friend. More so.
I was your student, sir.
Yeah, so from the Andhra University. It was always my pleasure to listen to you, Dr. Dayasagar, and more from the mathematical, morphological, the work what you carried on a simple DMs, what we always used to study, and you have taken to the level of applications. I was particularly interested to listen to you on how the dunes, you can use DEMs to get into the dynamics aspects of the movement of the dunes, which is very, very wonderful and fundamental. And I look forward to more of your talks, and I'll try to arrange some of your presentations to the academia in the other universities where I traveled. Dr. Shun, I think I congratulate you for the wonderful presentation on relating the geodesy and bringing in a lot of aspects of climate. And I was very happy to see a lot of examples coming from India, particularly in the forest fires and then floods, and some of the water level observations which you have taken using the satellite geodesy. So I think overall, and Dr. Lakshmi, I think thanks for the offer giving to me to speak a few words. And of course, my mentor, Dr. Professor Dikshitlu, I was very happy to listen to you, sir. And very nice.
Thank you, can we close it? We are just
nice. We look forward to some more of your similar presentation, Dr. Murali Krishna.
Okay, thank you. Every month we'll have the same program on 12th. May I request our respected revered president of remote sensing commission 3 of ISPRS to say a few words before I say vote of thanks.
Well, so many things have been said. Two very interesting presentations. I think it's important to have at the same time the information about sensors and acquisition systems, and at the same time algorithms and ways, strategies to describe the Earth surface. So this is very, very interesting. Some presentations are only on sensors, others are only on applications. I really enjoyed a session like this one, an event like this one, mixing the different aspects, because you cannot really deal with the interpolation strategies if you don't know about the origin of your data and so on. So really a good mixture of two presentations once again. So congratulations to you, Professor Murali Krishna. This is a very great initiative going on. This is the fourth webinar, and I invite all people here present here to be here with us in 1 month, because every month we have 1 hour and a half, about approximately 1 hour and a half. Very exciting. So thanks again, and thanks to Lashmi and her team. This is a very valuable help too. So thank you very much.
Thank you, Dr. Laurent. Just for the information of all, Professor Laurent is organizing a midterm symposium of Commission 3 ISPRS in the month of November at Belém in Brazil. So I will only appeal to all the people who are here to spread this message and try to attend, participate as an author in this particular event. I think the last date has been extended by a couple of weeks time to around middle of April to April 25th.
I put the link on the chat. I put the link in the chat. Otherwise, just go to the ISPRS webpage. You have the five midterm symposia. You know that we have 5 commissions in ISPRS. The real work is done within the commissions. We have 5 commissions, and this year, 2024, we have naturally 5 events in Philippines, United States, China, Australia, and Brazil. So I'm organizing Commission 3 Symposium in Brazil. It will be organized by Brazil and France together, but on the Brazilian territory. And you are all welcome to exchange some news, scientific news, industrial innovations, from sensors to applications. So please look at the link. If you are interested, you still have 2 weeks to submit something. And I hope I will have the pleasure to welcome all of you, or most of you, in Brazil in November.
Thank you, Dr. Laurent. So I take this opportunity of thanking Dr. C.K. Shum and Dr. Dayasagar for an excellent session we had on addressing few issues related to satellite geodesy and digital aviation models, respectively. Thank you, Dr. Shum and Dr. Dayasagar. And I thank also our President, Dr. Laurent Polidori, for taking time and be available for this couple of hours time. And most important, the person who is from the behind, Dr. Lakshmi Thapa, who supported